Hello everyone, and thanks for joining me. I'm Matías Vara. I'm going to talk about ToroV, which is a kernel in user space or ToroV. Before to start, I would like to thank all the people that made possible FOSDEM this year. I would like first to present myself. I enjoy working on operating system and on virtualization. I have worked at Citrix, TTTech, and Huawei, and you can find some of my projects at my GitHub webpage. Before go deeply into the presentation, I would like to picture the use case that motivates this project. I want to talk a bit about microservice and serverless applications. One way to decompose a monolithic application is by using service, in which each service provides a functionality. For example, in this picture, I implement the application at left as three independent microservices. And step future is to implement this microservice as serverless applications. So it is the cloud provider who deals with the deployment. This presentation talks about how we can improve the deployment of serverless applications. In such a context, performance and isolation are keys. There are basically two mechanisms to deploy serverless applications, either by using containers or by using virtual machines. This mechanism should be able to limit host resources, prevent interference between applications and with the host, be efficient in terms of CPU and memory, and in general, these mechanisms are chosen based on a trade-off between the performance and security. By relying on these two parameters, let's analyze these solutions. When using containers, the applications run as a process on top of a general purpose operating system. This process has a limited view of the host resources. This is implemented by relying on C groups and namespace, which are features of the host operating system. The application still communicates with the host kernel by using syscalls. This deployment is very efficient. However, the host kernel is exposed, so the attack surface is large. For example, a bug in the kernel host could be used to compromise all the containers. In this sense, containers do not offer a complete isolation. Instead, virtual machines provide a stronger isolation. To create virtual machines, we require a hypervisor that will handle the virtualization features of the hardware. In this case, applications run in a virtual machine on top of a guest operating system. In this case, only the kernel in the virtual machine can be compromised. However, a virtual machine requires a larger footprint because guests consume resources like memory, vCPU, and on-disk image. Also, the time to be up and running is longer than by using containers. These issues end up limiting the number of instances that a server can host. Also, this deployment requires a device model to provide hardware to the virtual machine, like for example QEMU. This represents a new component that is exposed to the guest that can be also compromised together with the hypervisor. The device model can be reduced by using approaches like Firecracker or QEMU micro VM, in which only a few virtual devices are exposed to the guest. To reduce the complexity of a general purpose OS and the number of resources that a VM requires for a dedicated task, some approaches propose the use of a unikernel to host microservice. A unikernel is when you compile the kernel with the user application. Currently, there are different unikernels which are used in different scenarios like Toro, OSV, Mirage OS, Unicraft, NanoVMs, and so on. In this context, we wonder if we can just offload the guest kernel in the host. This is called a kernel user space because it is just a process in the host serving requests from to the guest kernel. But what I call a kernel in user space, well, it is a way to offload guest kernel to the host. In this design, the VM does not need a device model. Conversely, instead of exposing a whole device model, we expose some high-level service to the guest. In the following slide, I'm going to present first user mode Linux and Gvisor and show the difference with ToroV. In user mode Linux, we have basically two processes in the host. One process that hosts the application and another that intercepts the syscalls. The interception mechanism is based on ptrace. The process that handles the syscalls emulate the whole Linux operating system. So basically we have split the user space and kernel space into two processes. In approaches like Gvisor or in ToroV, the application runs as a VM on top of a simple kernel and still communicates with the guest kernel by using syscalls. However, this kernel may decide to forward some syscalls to a process that is running on the host. This is triggered by a VM exit from the guest operating system. In the host, this process emulates the service that a kernel will offer, like file system or networking. Such service will be provided by using a minimal interaction with the host kernel. The reason to do this is to reduce the attack surface as much as possible of the host kernel. This is the case of Gvisor, which is a project from Google. In Gvisor, the serverless application is running in the context of a VM in Ringo tree and communicates with the guest OS by using syscalls. These syscalls are trapped and then forwarded to the host process named sentry. This component does part of the syscall and delegates file system syscall to a service named Gopher. These two components interact with the host kernel with a reduced number of syscall, which short the host kernel attack surface. This approach increments the cost of a syscall, so applications that heavily use syscalls may perform not so well. Well, in this context, what is exactly then ToroV? Well, ToroV is a minimalistic kernel in user space in which syscalls from the guest are forwarded to the host. It allows the user to configure what syscalls are allowed per application, and it provides a modified stdlib that the user application must be compiled within. It exposes a proxy API based on hypercalls to the guest. It runs in the host as a containerized process to reduce host attack surface, and it allows the user to debug this application by simply using GDB. In ToroV, the application runs in the context of a virtual machine, and when an application requires a service from the host, it calls the corresponding syscall, we trigger a hypercall. This hypercall is trapped by a component named virtual machine monitor, which processes the syscall. For each application, the user set up what are the syscalls that are allowed. This is configured by using a JSON. For example, the JSON that you can see correspond with the configuration for the HelloWorld example. In this case, only the IOCTL and bright syscalls are allowed. The user can also configure if the process that hosts the virtual machine monitor runs in its own PID namespace and root directory. So to build an application that runs in ToroV, we base on a modifying glibc or FPCRTL depending on the language that you are using. The application compiles into a ELF64, and from this file we generate a flat binary which is going to be loaded into the VM. When the application starts, the VM is in 64 bits load mode in ring 0. So in this sense, the virtual machine monitor is just a wrapper for the KVM API. The following pictures shows the memory layout when the application starts. This is built by the virtual machine monitor. If we read the picture from left to right, we have first the page directory table, then the application binary, the heap, and the stack. Currently, we are limited to 2 MB for the application binary and less than 2 MB for the heap. In the current version, the heap is pre-allocated. This means that syscalls like nmap just increment a pointer and returns. The amount of memory that we allocate is 2 MB per application. This memory is accessed from the virtual machine monitor. So when a syscall has to be forwarded to the host, the virtual machine monitor just modify the address of the parameters to point to the corresponding address in the host process. Let's see this in an example. So let's see what happened when we launch the HelloWorld example by using strace. In the first line, you have the command line that you can use to get the same output. This is a partial output in which I just highlight the most important things. We can see in the first line in green, the virtual machine monitor create the vCPU and then create a child process by using clone. This is the process that will intercept the syscalls from the guest. This process will have a limited view of the system by setting the corresponding flag in the clone syscalls. Then the child process changes the root directory and execute the vCPU. The first interception corresponds with the bright syscall, which we can see in red in the RAX register. Then the virtual machine monitor triggers the bright syscall but in the host with the corresponding parameters. These are some numbers for the HelloWorld application. It consumed about 1.5 megabyte of memory, and it takes about 7 milliseconds to execute. This is in average. The cost of the bright syscall is about 10 times slower than in the host, and this is due to the different steps to perform the syscall from the guest application to the host. So as we can see, ToroV is still a proof of concept, so there is a lot of work to do. These are some of the tasks that I have in mind for the future. If someone is interested on helping me, feel free to contact me. For example, I'm currently working on porting libc, and I would like also to port other languages like Go or Rust to ToroV, so we could generate binaries that instead of using a syscall, do a hypercall and interact with the host. And I also researching about comparing ToroV with seccomp. There is also the possibility to run binaries without recompile it, but by replacing the syscall instruction with some instruction that could trigger a VM exit, like the out instruction, as I'm doing now. Also, the idea is to maybe port the whole project to Rust. Um, to try to work on the syscall's bottleneck, which is where we spend most of the time. There is the idea that I could replace the asynchronous mechanism of the syscall by something that is, sorry, the mechanism that is synchronous in the syscall for something that is asynchronous, like for example a virtual device for syscalls. So in that case, the guest application will send packets by using virtues in which have all the information for performing the syscall in the host instead of executing an instruction that block the guest. And also regarding how it is implemented in the host, I would like to try to be more modular, so maybe to support different um, binaries coming from different operating systems. We would like to handle in different ways the same syscall. So to do that, maybe we can split the virtual machine monitor in components that handle differently the syscalls. This is still a proof of concept idea. If you want to see more interesting examples, here you have a couple of them. I think one of the most interesting examples I have is the Echo server, in which you can see the use of the socket syscalls from the guest application. Also, in that example, I show how I use GDV to debug the application. And the reason why I can do that is because ToroV includes a GDV staff. So any application that you run on ToroV, you could debug it by using a GDV client. Well, that's all, folks. Thank you very much for listening to me, and I will be online for questions. Thank you again very much. I have a question in which Leo asks why Pascal, and I don't have a good answer for that. I just like the language, but one of the future work is to replace it with Rust. Yeah. Have another question from Leo too. It said, do you think it will scale at some point? Well, I'm not sure. And if you compare with ShiftVisor, at least some papers say that in ShiftVisor you have a factor of 100 instead of 10 times. So I think depending your use case, you can tolerate that, but I'm not sure yet. Well, Stefan is asking if I have implemented something like the Linux VDSO, where the syscall is actually handled inside the guest as a performance optimization. No, I didn't. And the reason why I didn't do that is because I wanted to have a minimal guest.